בוקר טוב לכולם, לכל המשכימים. אני חושב שאתם שומעים אותי.
כן, שומעים. בוקר טוב.
אוקיי, אז אנחנו עכשיו נעשה סוג של המשך לשיעור הקודם. אז מבחינתי אני לא ממש מלמד חומר חדש, אני רק מרחיב על החומר שהיה בשיעור הקודם. אה, אני מקווה שתהנו מהשיעור הזה, שזה השיעור האחרון. אני נהניתי מהחלק הראשון של הקורס לפחות, ולצערנו הייתה מלחמה, אולי לא לצערנו לאור התוצאות. אז שוב אני מאחל לכם כל טוב. יש הערות כלליות לפני שנתחיל? אוקיי, אז
רק
אנחנו,
אנגלית,
yeah,
כנראה.
okay, sorry. We are talking about radiation. Um, so I'll just remind you briefly what we had previous class, and then we'll generalize this scenario for more general case. So in previous class, we had some charge QT and some minus charge also QT. This is a dipole. This is a dipole, which is an electric dipole. While in the homework, in the homework session, the teaching assistants taught you what happens when you have a magnetic dipole that is oscillating in time, and then it radiates. However, the radiation from the magnetic dipole is weaker compared to the electric dipole. So we are going to consider only the electric dipole. Now, this object can be considered also as a small antenna. If you want, you can look at it as a small molecule that is excited by some input of energy, and you have oscillations. And here, what we took is QT is oscillating with frequency omega. So the frequency omega is an input that is given by the experimentalist, by the system itself. We don't say how it is created. Someone is oscillating. The charge on top is going to the bottom and vice versa. And it's doing so periodically, in a period of given by this frequency omega. So this frequency that is in principle controlled by the experimentalist will eventually give you the radiation at the same frequency. So frequency in, frequency out. But the point is that the energy that is coming from the radiation can be not localized in space, but rather you can transmit this energy via radiation to far away, and thus forming some form of communication. So for this dipole, we had the typical scale, which was D, and we considered an observer which is very far compared um, to the size of the dipole. So R is the distance between the origin, which is located here in the middle here, and the observer. And the most important approximation we did is that the distances are very large. And in this case, you can easily understand that the fine structure of the charges is less important. Indeed, that was what we showed. Our tool, which is the main tool here, is the retarded potentials. The potentials are two potentials. One is the vector potential A, and the other one is the scalar potential V. But we are working in the Lorentz gauge, and for example, for the calculation of the electric field E, we need both of them in principle. The derivative of time of the A, of the vector potential, will give you a component in the electric field, because all the problem here is a time-dependent, non-static problem. And with retarded potential, the key concept was the retarded time. I will talk about the retarded time a bit more, but basically it says in a very general sense that the information from the dipole is reaching the observer in a speed which is the speed of light. So the velocity of light, c, is an important quantity in this theory of radiation. So we are talking about relativistic effects, but we need to distinguish between two types of relativistic effects. First of all, the radiation itself is relativistic because If we just take C to infinity, then there is no effect. But there's also a question how fast the particles inside this inside this region are moving. And today we are going to treat mainly towards the end of the class, mainly the case where this velocity here, not to be confused with potential, is small compared to the velocity of light. So it's a semi-relativistic effect, but it's true. The radiation is relativistic, but the velocity is not necessarily so. Anyways, what we were interested is in this problem that we had previous class. We had this direction Z, which is the direction of the dipole, which will determine the direction of the radiation. In general, we do not have a specific direction D. If we have some accelerating particle moving in all kinds of directions, we will not have this in general. And then what we were looking at is eventually is this quantity which we called P. This is the energy per unit time. It's a scalar that is emitted through this radius R. And again, R is very big compared to the size of the dipole. So what we have here is a flux of energy going outside, and from conservation of energy, we immediately understand that someone needs to supply the energy. And the person who's supplying the energy is the person who's changing the configuration in time, let's say in a periodic way. So you have some dissipation because you have some currents, and then there is input of energy to the antenna here locally, which eventually goes out. So in principle, when you are running and you have dipoles and you are accelerating especially, or let's say you are running in a kind of backwards and forwards like a cosine function, so to say, you are emitting radiation. However, of course, for human beings, this radiation is totally negligible because essentially you are not charged, and also compared to other input of energies, this is totally negligible. So there are special circumstances that this energy becomes dominant, and this is, of course, when you have charge systems that are accelerating relatively quickly. And only then radiation is important. But in principle, you are radiating all the time, but it's really ridiculously small amounts of electromagnetic energy. Anyway, so acceleration gives you radiation. That will be the acceleration of what of the charges here. This gives you radiation. If the particles here are just sitting and not moving, we are in electrostatics. There's nothing happening. This is obvious. But even if they're going at a finite speed, which is constant, we don't have any radiation. Only when you have acceleration do you get this effect that the particles, the charged particles, will emit light. This we will see later towards the end of the course. But going back to what we had in previous class, what we wanted to say is the following. We have this P, and this P is related to the Poynting vector. So again, I have this imaginary sphere where the observer is sitting on one point, and there is some element of area, which is a vector dA, not to confuse dA with the acceleration coming later. So this will depend on, it's a vector, it's a normal to the surface as usual. We had this many times in the course. And then what we need to calculate is S, which is the Poynting vector. This was E cross B divided by U0. This is a vector, and this vector is going to change whether or not you are here, 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 or here. And once you have this S, via integration over the sphere, we get P. So S gives you the flux of energy at a point per unit time, per unit area. And when you integrate over the whole area, you get the total energy. So P and S were in previous class were very important quantities, and we discussed them extensively, especially S previously. So the general method that we need to do in general is we need to calculate the retarded A and the retarded V, that is using this concept of retarded time. From here, we get B, and from both of them, we get E. From both of them, we get S, and then after integration, we get the P. The S is a vector, vector, and vector. This is the general plan. These are these retarded potentials, Leonard potentials, that we already studied. The last 3 lessons were on this. So,
wait, Eli.
yes.
What type of, we talked about, I'm not really sure what type of radiation we're talking here, what type of model. I'm not, I didn't follow.
So in the previous class, we had a very simple model, which is given by this oscillating
Like
electric field.
one,
Excuse me?
like a one, we talk about a one, how we call it? One particle oscillation or a dipole oscillation?
So today, that's exactly my point. Here we are the dipole oscillation. And today I'm going to do it in full generality. It can branch into a single particle, a single charge particle that is accelerating. It can be a dipole, that is, the system is neutral. All these systems will emit radiation, but they will be different. So what we had in previous lesson was a dipole radiation. It is a simple and a special case. Also, the configuration in space were very simple here. Now we're going to do the general theory, okay? So now let us do it, unless you have some questions. Okay, let us remind me what we had in previous class, which is only for the dipole. We had this formula. So mu zero, it's not so surprising that everything is proportional to mu zero divided by C. So when this is written in this form, you can write it in several ways, but we write it as 1/C because just to remind ourselves that when C goes to infinity, the speed of light is infinity. Of course, in practice, it's finite. Then, of course, we will not have any effect. Then we have this P0. And P0 was in previous class, this Q0 times D. So here enters the dipole moment. This is the magnitude of the dipole moment. This is only for dipole and only for oscillating dipole. Then we add omega squared here over 4 pi. Okay, there are numbers that you need a calculation. You have this famous sine theta divided by r, cosine omega t minus rc. All this squared. So again, we calculated E, we calculated B, we multiplied them, maybe skipping some of the information, and this is the vector R. So S is a vector, of course, and it's pointing outwards towards R. Again, this is the Z direction. And you see this sine theta, meaning that if you are here and the dipole is in this direction, then there will be no flux of energy. You will not be able to receive the energy. But if you are here, the radiation will be maximum. So this is the sine theta effect here. Here you see, so here min, S max. This is the retarded time in this approximation. It's an approximation, of course. When I say retarded time, there are actually 2 retarded times. This is retarded time after we integrate. But this is what I mean, that it's not that you care at time t at the oscillation of the dipole at current time t, but you need to care about the time the retarded time, which is T R minus R over C, and R over C is obviously the time of propagation of information from the dipole to the observer. So you are looking backwards in time in this formula very easily. And the important part is that here we have 1 over R. And with this square here, we have 1 over R to the power 2. This is super important because, as we said in last class, when we integrate overall space to get P, the integration involves an R squared when you have this dA. And then this will give you a finite radiation in principle also at infinity. So it doesn't matter how big this sphere, this P, this total radiation is given by U0 P0 to the power 2, omega to the power 4. Okay, there are numbers 2 pi, 12 pi over C. So what is happening here, you see this P0 is squared, so it's the dipole squared. And you have this dependence on frequency. And we want to understand a bit better why it's frequency to the power 2, but to the power 4. This has many consequences, which we discussed, for example, for the scattering of light, the color of the sky, etc. We discussed all this, but you see this point is independent of R. And this is because of this 1 over R, which is a very slow decay, and it's a very surprising decay because in statics, usually fields, both E, if you have a charge and it's static, the field E will go like 1 over R, and then you do not expect any, in static case, you do not expect anything. And indeed, when W is 0, which means no time dependence, indeed, there is no effect. What is W squared in the context of an oscillator?
It's
proportional to
independent to the it's in the
right, but it's independent of W squared, but
it's proportional to the
no, it's proportionate. It's dependent on the type of the oscillator. If we're talking about the classical harmonical oscillator, it's proportionate to the to 1 over m, to 1 over the mass, if you will. Of course, you have the
yes, of course, but I'm not talking about the
constant
definition of the oscillator. So of course the frequency of the oscillator is given by the spring constant, if you want, and by the mass, as you say. But where what does W square remind you? Maybe it doesn't. Maybe
the acceleration.
The acceleration, right? So if the amplitude, let's say, is cosine omega 2, omega times t, then the velocity, you take the derivative, you get one frequency out, and then you take the second derivative, it's omega squared. So what we see here, if you have some imagination, is the acceleration squared. And we are going to show that this is general. For this specific system, the acceleration is proportional to omega squared. Why is it proportional to omega squared? This is because of Newton's equation, actually. You know, the K is proportional to this omega squared, the spring constant. So we more or less see, if you read Griffiths already, you more or less see some form of acceleration here. And this is going to be the theme that I'm going to discuss now. So if there are no questions, I'll just start solving the problem in generality. Now, if you go to Griffiths and you look at it, and it's a pretty horrific calculation because you need to go through all these steps, A, V, calculate B, calculate E, calculate S, then integrate to get P. I'm going to do some shortcuts. I hope you appreciate them. Based on some physical motivation, just to make things simple. But first, let us define the problem. So I have some region in space, which I draw in a kind of an abstract way. And in this region, I have some charges, rho, and I have some vector potential, I have some currents. This is a problem in 3 dimensions, the current, the usual current J, which are functions of time. So these are functions of R and time t, and the same for the density. We, of course, know exactly what these things are. Given these, let's say someone gives you these objects, and then later we can solve very special cases. The question is, what is E? What is B? This actually we know this from the formalism of Leonard, where we have these retarded potentials and retarded vector potential, and then in principle we can get E and B. So we need to calculate A, we need to calculate V, and then we need to get E, and as I said already, from here we can get S. So this is our mission, but let us stop for a second and let's do a trick, which is a physical trick. I don't want to calculate everything. I would not like to calculate both E and B, too much work. I would not like to calculate both A, the vector potential, and V. So how can I hand-wavingly maybe avoid this horrific calculation? Anyone has an idea? Just reduce it, let's say, by half.
Maxwell equations?
Yeah, everything is Maxwell equations. We are going to solve that soon, but I say we need
Maybe
to
you can solve only AA.
know how to do it in general, but I want to I want to make the calculation shorter, even though maybe I'm omitting some rigor.
I don't sure, but maybe you can calculate A, and from A you can derive B, and you also know the direction of propagation. So we can from both B and K you can derive E, and from these both quantities you have S, I think.
Perfect. So you stated it very clearly. We do not want to work hard. We are very lazy. It's summertime and you should all go to the beach and enjoy life. So what we're going to calculate is we're going to calculate A, and A will give you B, which is rotor A. Remember that E, the electric field, you need to calculate both A and V, right? Because you need the time derivative of A to get E and also the scalar field V. So I'm just calculating this, then I get B, then I'm going to say E and B are orthogonal one to another and orthogonal for the direction of K, as the student just now said. And we also know the relation between E and B. What is the relation? The relative strength of E and B. They are not in the same direction, of course. What is it given by?
C.
C, yeah, the speed of light. So that solves a lot of algebra, but interesting algebra. I'm not saying that it's not worthwhile doing the whole calculation. And this is, again, this is done in the textbooks, but I want to make a shortcut. It's like when I check exams, usually people, they go on the long way, and then some people go on the short way. And then the people who go on the long way will always get tired and make mistakes, and the people who have these shortcuts can solve the exam pretty quickly. I
Can
find
I
it.
ask a question about this trick?
Yeah.
How can it be that no matter which charge density you are putting in the system, you will get the same E? I mean, the only information you are using to calculate A is
No,
J.
no. This I do not say this. I say
Okay.
A will depend on J.
Okay.
Let's write down A. A depends on the details of the system for sure. And we will have here a very wide platform of theory, which will give you a very wide and rich behaviors of these fields, E, B, and S. So the physics here is very among us, but my point is I'm just going to calculate A, and you'll need to believe me that what I say here is true. And this is, we said it already, because we said that, you know, we care about, this is the system, and we care about the observer that is here. And here we are in free space, and we know that Maxwell's equation in free space have these properties. So more or less, you know this. We didn't prove it rigorously maybe, but You know all this stuff. Okay, so what do I need to do? I need to calculate A. So what is A, R, and T? We had this formula. This is a super important and super general formula that we already studied. You need to integrate over the volume of the physical volume where the charges are present, right? And the A is given by the J and only the J, R prime, T minus, okay, let me write it down, R prime over C divided by R minus R prime d tau. D tau, as usual, is an element of volume inside this, inside the material. So this is d tau as usual. And this equation is well understood. By now, let me remind you, we have here, if we have no time, this guy is, let's say, is simply zero. There's no time dependence of the current. Then we are in the static, and this is essentially the Biot-Savart law. And the Leonard potentials that we studied say, instead of calculating J at time t, we calculate it at the retarded time. This retarded time that I have here is different than what we had above, because the retarded time that we had above did not depend on R prime. It's a bit confusing, maybe the notation. You see here, this one depends only on R, but this depends also on R prime. But again, I think the physics of this was explained already. So it's a very complicated equation because at every point R, there is a different R prime. This is R prime. There is a different R maybe. So when you are integrating, you are changing R prime. So the integration over R prime is inside this d tau. Okay, so we already discussed this. And then we want to solve it again at very large distances only there. I mean, in principle, you can use this formula and then calculate also for near field effects. Near field effects means close to the system. This is my system. So if I want to walk very close, I can use this formula, of course. But then usually it's very difficult to solve it because of the retarded time. Even in statics, it's very difficult to solve it. Okay, so what do I do? The first approximation, I have this R minus R prime over C. This is the retarded time, right? What happens when R is much, much bigger than D? And what is D? This is my object. D is the scale of this object, D. It doesn't have to be round. It doesn't have to be a dipole. It's some region in space where my particles are moving. And this is a confined region in space that will be important. They do not approach the observer that is far away here. So what we do in this case, you see the R prime, we integrate over R prime here. So what do we know about R prime? If the origin is somewhere here, R prime is always of the order of D or smaller, right? Do you understand this point of view? It's very simple. I integrate over the volume where the charges are. So R prime is of order D, even though it's an integration variable, I can write as an approximation, this is T minus RC. This is a leading approximation when this condition holds. And this is exactly what I'm going to do. So I'm going to replace in the integration T minus R over C. It's true that inside the small object, there are different locations where different locations send the information different times. They arrive at the observer. But imagine you have a star that was created 10 light years ago. It doesn't matter from point of view of the arrival of light to your eyes if it arrived from one side of the star or to the other. It's more or less the same time. I think this is pretty obvious. So this is approximation number one, and then we have approximation number two to leading order. Of course, you can calculate corrections. This is 1 over R, because again, R is the position of the observer, R prime is the integration variable and we are inside the medium, this is always smaller than d, and then we have here 1 over r. So these are easy approximations, and then what we get, A RT, I'm going to write it more or less equal in this approximation, mu 0 over 4 pi r. Here I managed to take out this one. Now I'm just removing the r prime, so it's easy. I integrate over the volume, j of r prime, and now t0 d tau. So this is the equation we are going to work with. This is an important equation. And t0 is simply t minus r c. I know if I'm somewhere in space, I know precisely what is this t0, depending on my location and depending on the time t, which is the clock running in the laboratory. So now the integration is much easier because the integration over d tau is only over this r prime here. Of course, you may or may not, the function itself can be horribly complicated, but then we are going to claim the following. So this is a physical simplification, but it's exactly the same. So let's call it I dipole approximation is going to be equal. It's the same thing as this guy. It's the same. This is equal to this thing. This is a claim, u0 over 4 pi p dot t0 over r. Again, within this approximation that there is other approximations we are going to mention, d is much smaller than r. Later I'm going to discuss other approximations. And what is this p? This p is the dipole moment of what? Of the object. We have some object, we have charges inside the object. This is the dipole moment, and it is defined also for charge systems. So it's a dipole, but the total charge can be either 0 or it can be something. This is a general statement. So in principle, what you need to do is find the dipole moment of the system, and it's a vector, of course, because also A is a vector. And you need to take the dot here is a time derivative. But then you need to calculate this time derivative at time t0. That is in the retarded time, of course. So the value of the time derivative of the dipole moment gives you A, and eventually this will give you E, the electric field, B, and S. Okay, so the first question is, why is this correct? So what is the dipole moment? This is just a definition. This is QI, RI. In principle, RI at time t0, but I'm omitting the time t0. I think you all agree this is a reasonable definition of a dipole moment relative to some reference frame. The reference frame eventually is not so important because we're taking eventually the time derivative. So plus a constant is not going to be important for us because of this dot here. Okay, this is the definition of the dipole moment. So what is P dot? The P dot that we have in the formula. This is by definition sum over I. Again, what I'm thinking about is a system and you have many microscopical charges inside. Later we can smooth this, make an integral out of these localized charge. But we know that in principle, real charges are, we treat them here as discrete, not continuous. Later, again, we can go to continuous approximation if we want. But this, by definition, I just take the derivative of r, which is the velocity, of course, of each one of the particles inside the volume. It can be, again, very complicated. And in many cases, we do not know this. What is J? J was in our formula initially for the A. So we need to express A. What is J? Also, this was part of the course. In general, in the continuum, it was given by this equation. This is J, which is local in space and time, and a very specific space and time. But when you think about rho, what is rho? What is rho? We studied this at the beginning of the course when we studied electrostatics. What is rho in this language? It's going to be a sum of delta functions in space where each charge has some position in space. So what is this? This is simply, by definition, a sum over delta R in space. This R eventually is not the R where we observe it. It's going to be R prime because we need J of R prime here. But just write it generically as R. This is R minus R I, the position of the ith particle. I'm summing over all the particles I have here, n particles. They can be Avogadro number of particles, I don't care, multiplied by Qi Vi. This is the microscopical definition of currents when we don't cause grain. There's no averaging here. Again, this is an old equation in this course. And then what I need here to look at is at P dot. Then I want to say, is this, that's the question mark, is this equal the integration over J over R prime, J of R prime? Again, remember R prime goes with the integration over d tau. As usual, usual definitions of this course. Well, I just need to plug in this delta function, and even I can integrate over a delta function. This is equal to, you see these Qi Vi, after the integration of a delta function, I get 1 over d tau. So this is Qi Vi, it's a vector. Again, the velocity, sorry, no. Yeah, this is one. But this is equal exactly to P dot. Okay, QED, we are very happy. You see, this is equal Q dot because this guy here is VI. Ri dot. By definition, the derivative of the vector Ri is the velocity of the particle. So we eventually see that this guy is equal to this guy. And this is exactly what I did here. Up here, I replaced this integral by this object. So it's a nice, yeah, this is simply the dipole moment of the system that is changing in time in principle, and we take the derivative. So let us look at a special case now. Now it's a special case. I want to say, let there be a wave. How do we generate wave? Well, how to generate wave? Well, all what we need is some dipole in general. It can be the dipole that we discussed in previous lesson, but some P dot that is proportional to EI omega t. Okay, at time t. But this means that P dot at time t0, that is in the retarded time, which is the time that I care about. I don't care about time t in the formula above. You see, this is at time t0 here. So at the retarded time, what do we have? We have EI omega. Let's write t0, t minus r vector over c. But what do you see here? We see, first of all, A, for example, A, but it will follow also for E and B, is proportional to P dot, which is proportional to EI omega t minus R over C. But this is, of course, what you already know from free waves. But the difference is that now I did not put these free waves, these spherical waves, actually, these are spherical waves. I didn't put them in by hand as a solution of the Maxwell equation like we did maybe in chapter 9 or 8 of the course. You remember this? We looked at solutions which are free waves. Here it's different, I claim. We are generating it. We are generating the waves. And this is what I mean, let there be a wave. We are creating the wave. And how are we doing it? We need a system of dipoles, P, and we need it to oscillate at some frequency, omega. These are clever experimentalists can do that. And in fact, we did it theoretically previous class. But once you have this A at, and this is the point. This is at point R, far away from the place where the dipoles are situated. You have this propagating spherical wave. So this is beautiful. And where did these waves that you are familiar with, or where did it come from? You see that it came from the retarded time. So the retarded time at least according to the theory, gives you these spherical waves that we are all familiar with. And of course, if I define the vector k as W over, this is C here, we have the usual relation between the wavelength or the wave vector. So you can write it with lambda instead of k. And this is, we don't need to put in k because you see this is this omega divided by c. This is the k by definition. It's what appears here. So here you see that this famous relation that, again, you studied this previously between the vector, the frequency and the vector and the vector k is due to the retarded time. This is what I want to emphasize. The retarded time effect gives you this effect when you generate it. Of course, it's also an effect that you can see by solutions. If you postulate a solution of the Schrödinger equation that is a free wave, you'll also get this. And this is what we did here. But again, now we are creating these waves, and this is a very generic feature. So now we have this, what we said at the beginning of the class. Let us assume this plus here is perpendicular to. And again, I can, in principle, I can calculate this A, gives me this B. I calculated now this A in general. I know that E is B over C. Again, from solution to Maxwell equation. And since I have calculated now A, formally at least, this is this equation here, then, okay, I need to take the rotor. I'm not saying this is totally easy or totally different, but you're already experts in these type of problems. We will be able to solve the problem. But before doing that, the nature of the approximation. So again, let us assume this is only for oscillating fields. Like in the previous example that we had up here. So 1 second, I'm turning on the air condition. It turned off. So let us look a bit carefully. I hope you can follow in the integration we use the following. When I say integration, I mean the integration over J, the exact J. So in principle, for an oscillating field, that is a frequency that the dipole moment is proportional to this frequency that is oscillating. This is not the general dipole yet. So what did we say? This is in principle, inside the integral is this object. And then I said, let's replace this by omega t minus r over c. Right? This was the retarded time t0. And of course, this is valid, as we said before, when r prime is less than r, then this means that d is much less than r. This is fine. But if you think about it carefully, because you have an oscillating field here, it's not enough to assume that r prime is smaller than r, because if you gain some phase in general, the cosine function, if the phase is big, you cannot really ignore it. So we are also doing another approximation here. So let me write an expansion. Hopefully this is clear, which is not rigorous, but I think it's clear. And I would like to say that this is to leading order what we did before. This is the T0. But now I expand it and I do it very kind of sloppy way. What will be, what am I doing here? I'm taking R outside of the object here. And then inside I'll have R prime over C. And then this will be R over R prime C. And you see, this is a small number, right? So because of this. So there are more terms. But if I cancel this one and this one, then I want to say that omega R prime over C, see, this is this omega, is something small. Right? So this must be less than 1. This is a dimensionless quantity that is less than 1. But what is omega over C? That's lambda, right? So what we define, we see here R prime. Again, the integration variable is less than D. Sorry, less than lambda. And this means that D is much, much smaller than lambda. So we used this already in the previous example, but this is a second approximation. So you put in some frequency. This frequency with the speed of light will determine what is lambda, this wavelength. This is given by this guy. This gives you lambda, as usual. And whatever the frequency is, you can get different lambdas. And for different system size D, you have different sizes, but you need to have this condition in order for the approximation to still be valid. Okay, now go back. Let's now calculate B. Well, we'll not calculate it because we calculated already A. So taking the rotor is an operation of taking derivatives. I feel it's not suitable for this last class. I just give you the result because you already know how to do this. 4 pi RC R prime cross P second derivative at time t0. So this is the dipole, and this is the electric dipole approximation for the B, or this is how I like to call it. At large distances R, it doesn't have to be maybe the word dipole is confusing because it can be also a charged particle. It's a generalized dipole. So this is the formula that we get here, but there was, maybe someone can say that I used another approximation. So when I take the rotor of A, this is my A. I need to take derivatives with respect to R. And where is R hiding here? It's hiding in here, but it's also hiding in the retarded time. So when you take the derivatives, you need to ask yourself which one of the two terms or which one of the two derivatives is more important. And what did I say here? Look at the final answer. What am I saying here? It has this P double dot, right? The second derivative. So what does it mean without proving at this stage? It means that I care about the R inside the retarded time, and this R is not important. The physical reason for this is the following. When we'll take a derivative with respect to R here, what will we get?
1/c.
That is actually from the other term. But when we take this one, we will get 1/r.
1/r².
And that will be decaying very quickly, even though 1/r² is not an exponential decay, but it will be much, much faster decay in space compared to the derivative that will come from this T0. Because what is the T0? I'll soon write it down, but you'll see when you take the derivative, of course, it's a rotor. It's a bit more complicated than what I'm saying. When you take these type of derivatives in space, you have the internal derivative, then you get, instead of a dot, you get double dot. And then you need to also take the derivative here, but that will give you 1/c. But we know that 1/c is a good thing because we had it in our simple example in front. So this is the important. So there is a second approximation. I'll soon say it, explain it again in slightly more mathematical detail. But now let us just look at this equation. So again, here we have the retarded time, which by now is expected. If P is, let's say, in the Z direction, then R cross P is in the phi direction. So if we have a dipole in the Z direction, you immediately see that this is in the phi direction. But in general, this can be describing many complicated things. I have this sign here, Gimel, in my notebooks. So I claim that P double dot is acceleration. This you see from the definition of P. Here is P dot. What is P double dot? So immediately you see P double dot will be QI RI double dot. This is why I call it from acceleration. It's not just general acceleration. You need to sum over all the particles in the system with different charges in principle. Each one of them has a different acceleration, QI, AI. This is A, acceleration, I, in principle. But let's say you have one particle in the system. So the sum here goes not from 1 till n is equal 1, there's one particle. Then this will be exactly the acceleration of that single particle. And that is the meaning of this P double dot. So you see here, acceleration is going to be important. We see that B, as I mentioned already, goes like 1/r. Hence, radiation, if the same is true for E and the same is also true for E, the electric field can be transmitted far away. More correctly, the P the P, the energy per unit time emitted through a sphere that is situated at distance r far away from the source is going to be a flux of energy that is constant in time. It's energy per unit time, but that itself is independent of time and independent of the radius, like we saw in our previous example. So this is similar to the previous example. Of course, if c to infinity, b in this approximation is of course 0 because you just kill everything here, and 1 over c goes to infinity. To see this a bit mathematically, how I got this, without going into all the details, the rotor of A using, so I'm just using a integration of a function, right? And this is what I'm using. So this is 4 pi r. So I neglected operation on 1 over r. What do I mean by operation? The operation of the rotor, since it is not important for large r. It will give you 1 over r squared terms, as I mentioned. This is rotor P T0. This equation itself, rotor A in this approximation, just a well-known equation, let's put it this way, 4 pi r. This is the decay 1 over r that we are looking for. Div tr0, div t0, it's div with respect to r, of course, cross pt0. Here I just use a well-known equation, which is the following. What I'm using here is essentially an analog of this. F t of x is f t of x d t dx. So you see this is the same as this. You did such derivatives many times before. Here I have double dot acceleration. So I think you all can see where it comes from. It's the internal derivative. It's a function. A is this is a function of r inside here. And then I need the internal derivative, which is here this div. And this gives you the result above, because dt0 dr will be proportional to 1 over c. This gives you the 1 over c because t0 has a term which is 1 over r. I think this is a simple explanation. So again, we see that everything here is because of the retarded time. If we had here, instead of time t0, we had here time t, all the effect would be gone because we could not take the derivative here. So retarded time is the most important concept here that gives you this effect, again, with which you can send information practically freely over very large distances. What is E? From the above arguments, it's simply the following. Let me copy this. This is 4 pi r. R vector. So again, remember, we are at some point r, so there's a vector r in this direction. This is not the direction of the field, electric field, because the vector pointing is in that direction, as we know from a previous example. This is cross r at cross p0 t0. So this gives you the orthogonal to B and orthogonal to S, S is going to be in the R direction. This why this is reasonable. Of course, I'm not deriving here anything, but this is very reasonable. You see here the B essence. There is a C. Okay, the C goes away because the ratio between the fields is C. And then this makes sense. Again, this is what I called before hand waving. The general proof, again, you need to calculate the potential V, again, retarded. You need to take the time derivative of A. You need to go over all the math, but this is what we expect based on simple calculations. Now, let us see two consequences of this, and then we will end this class. So let us look at S, which again is E cross B divided by U0. And let us assume that P, this P, remember, this is not the energy flux, this is a vector, this is the dipole, right? This is the dipole that is changing in time. This is the sum of Qi, Ri over all the charges in my system. So this is the dipole of this system. Let us assume that is only one thing, that is in the Z direction. So the direction of this object is constant. This is the same as the model that we had previously, but now we are not talking about a cosine field or whatever field. This is just definition of the P. Now, if this in the Z direction, then I can calculate Z cross R. And also here, I can calculate, if this is in the Z, wait, where is, didn't I write? Yeah, then if this is in the Z direction, then I can calculate the B, I can calculate the E, and you get what you expect, that S is in the R direction. And then you can easily show, this is, I think, easy, using the above equations, that you get U0 over 4 pi. It's square. Of course, the numbers here, you need to do the calculation. P double dot, this is again the acceleration due to the retarded potential. This is the dipole moment, the second derivative in time of this. This goes like 1 over r squared sine theta r. So this is again the sphere, and it's going in this r direction. This is the flux of energy per unit time, and here we have a square. The square comes from the fact that from this definition of angles, from the fact that the dipole is in the Z direction and R, so R cross Z gives you this sine theta, and you have it twice, once from the E, once from the B. So we get this sine theta. Now this sine theta is exactly the same what we had in the previous lesson. So previous lesson, we had this dipole like this. And we got also that the radiation, if this is the Z direction, so maximum S, and up here minimum S. But this is, again, it's different than what we had previously, because now, except for the direction, because now we have the P double dot, whatever it is. I mean, it can be many things. I'm not even saying it's a function of time. When you have here an oscillating function, so P is proportional to some cosine omega t, then the second derivative will give you omega squared, and then you need to do it to the power 2. And that is because we multiply E and B, the electric field and the magnetic field, that gives you the power 2. And then you'll have here omega squared. So if this, then we'll get this famous S omega squared as in previous class. But now we have it in terms of acceleration, what I call acceleration of the dipole. So again, it's much more general. This R squared is super important because it's again related to the fact that both the electric field and the magnetic field decay like 1 over R. So when you calculate the vector pointing, it's 1 over R squared. And then when I integrate over R squared dr to get the total power, it will be a constant independent of R. It will not diverge, etc. So again, this is what we expect, and it's also what we saw in previous class. So if I integrate over R fixed, theta and phi, so I integrate over the sphere where the observer is sitting. So I want to calculate from S that I just now gave you, I want to calculate the power. So P, sorry, it's not a vector. Not to be confused with, so let us write it now, P power, not a vector, energy per unit time emitted all over the sphere. That is simply integral over the sphere, not where the object is sitting, it's the sphere of the observation, S dot dA. And this gives you, this dA gives you an R squared term, which will cancel this R squared here. And this is similar to what we had in previous class. And then this P, this power, energy per unit times in watt, is given by this expression. It's a simple integral because the integral over phi is simple, and I have only the integration over a sine squared here. So what is the integral I need to do? Is anyone out there? Eventually to get this result? B dot. I think it's clear what I mean by square. It's P dot, if you want straight. At time t0, at the retarded time, over 6 pi c. And the integral I need to solve is sine theta to the power of 3 d theta, integral from 0 to 2 pi, and this integral is 4 over 3. Y sine to the power of 3, I have this sine to the power 2, and then when I integrate over the angle theta, as usual, it's d cosine theta or d sine theta d theta. So this is just the usual integration over the angle theta that you saw a million times, and I'm using this number in the example. So this is the total power. It is independent of R, as I mentioned, but it is a rather, again, it's rather general. So let us now say, in addition, P is in the Z direction, but let us say that P of T is some P0, which is a dipole moment, cosine omega T. So this is a very specific case already in the Z direction. Then it's easy to show that S, but now I average. No, I actually don't average. I just use this equation up here. I can, if I know the P, it's an oscillating dipole. I can take the time derivative. And if I just plug it in, I get this U0 16 pi squared over C. Prefactors are not so important. W4. So this comes from second derivative of cosine omega t, and all this second derivative to the power 2. The power 2, again, comes from the fact that we have both E and B, so we are squaring. And that's why we get this omega 4 that was already in the previous class. It's not new. P0, the magnitude of the dipole to the power 2, sine theta, r squared r. And in principle, you have a cosine squared omega t0. This is an extremely fast oscillating function. Fast oscillations. So if I average this cosine, I get a half. It's cosine squared. I get this half, famous half. But I can leave it like this. I'm fine with this. We can think about this S not only as varying in space, but it's also varying in time. But the variation in time is usually not so interesting for us because it's very, very fast. These fast oscillations that we already discussed in previous class. So all this is the same that we more or less similar to what we had in previous class. Again, now we don't have these two charges anymore with Q that is changing in time. This is not needed, but essentially the physics is very similar to what we had in previous class. But now we can ask the following question, and here I'll eventually end. Let us say that P is some d of t times Q. So what is this? This is a single particle with charge Q, and it has some trajectory d of t. So this is a single particle. System is not neutral. When was it neutral? It was when we had the dipole. The total charge was 0. Now we are not, but with some particle, and in principle, this particle is accelerating. This is the P. So what is P double dot? It's very simple. It's Q times A of t. This is at time t, not at the retarded time, but we need to plug in the retarded time t. So A double dot is simply d, the position of the particle. And how is this particle moving? Someone is pulling it. I don't care who creates this motion. You created the motion. You drag this particle because it's radiation. You need to put in energy to do that, but that's fine. You are changing the position of the particle and it is accelerating. That is important. And then we get this E, and then we just need to plug in these formulas. This is the, I'm not showing this completely. This is U0 Q. The point here is that it is A absolute value squared. This is a vector, but it's absolute value squared at time t 0 retarded, divided by 6 pi c. This is a famous equation. It is the Larmor equation. It was assumed here, this is related to the value of lambda, that the velocity of the particle here in absolute value is still smaller than c. There are corrections to this. So while the effect is relativistic, the particle is not too fast. But my main point here, and I think it's a very good time to stop the course, is that this radiation, this loss of energy, is proportional to A squared. the acceleration squared. And why is this important beyond this course? Of course, it means that if you accelerate a single particle, it will emit light, and you can use that for all kinds of technological applications. But I want to end this with a big shadow that we have here on classical mechanics, and that is simply the hydrogen atom paradox. So in the hydrogen atom based on Maxwell, and everything that we did here was Maxwell, it was not quantum. So here we have a plus, a proton. It's not a PR. It's not the power, and it's not the dipole, it's PR. And here we have E, the electron, but it is accelerating, right? It's accelerating based on Newton, because this radial accelerating V squared over R, the radius. So if it is accelerating, then it has to emit light, emit radiation. And if it emits radiation, what happens to it? It will lose its speed and then collapse. And then the size of our bodies, we are composed of atoms which are similar to the hydrogen atom, would collapse, and we will all vanish, and all material will vanish, etc. So this was a big shadow on the classical theory of Maxwell. And the solution is, I think you know this, we need quantum mechanics. So the classical theory of radiation, while super important in any daily aspect of our life, also brings you to an end of classical mechanics in some sense. We need to think about more advanced theories, and the advanced theory in this case is going to be, at least for atoms, it's going to be quantum mechanics. Okay, so I think here I end. If you have questions, you can ask them now. If not, I'll briefly talk about the exam. Okay, so first of all, I have to say that I never had a course like this, in the sense of I had 4 TIs and 2 people checking the exam, checking the exercises. 4 people who are TAs. One of them is in reserve, is in the military service. Another one had a very nasty death in his family, so he had to retire. Another one is in India because of the war, and another one is getting married. So all the 4 are more or less evaporated. They still try to help me from far away. And then one guy who was checking the exercises, he also was recruited to the war in Gaza. So we had to switch him in the last moment, and it was very complicated. Now, why am I mentioning this? I want you to hand in on time your homework, because we are facing difficulties checking it. So there will be no delays. We will publish the grades of the homework, and you will have like 1 or 2 days to claim that maybe we made the average wrongly, or we lost something, etc. But after these 2 days, if you don't complain, this will be your official grade. And hopefully you can do it because I don't have anyone to help me. And I myself, I'm not in the country. I'm leaving to some conferences. So hopefully you can do it in these 2 days, and you know, in a civilized way. That is very important for you. So I hope to give you back the homework, and then whoever fails the homework, if you fail the homework, you fail the course. So you want to know your grade, because there's no point of you going to the exam if you already failed. So simply don't come to the exam. And this is why it is important for us to publish the grades of the homework soon. And for that, we need your help to hand them in exactly on time and don't complain too much. Now, people who are in military service, things like that, they should tell us. When were they not in the university. And of course, the average of their grades will not include these periods where they were absent. No one is expecting them to do this homework, but we need to know. We need to have this information. So please send your TA, your teaching assistant, this information in order for us to be able to give the correct grade for homework. Now, the exam itself, it will be 3 questions out of 4. So you have an option to choose. I understand that due to war, there was a lot of anxiety, I would put it this way, and people had their, maybe some of you real problems in the sense of your physical safety, etc., and surely some psychological effects. So I decided, following Yossi, it is very painful for me that radiation is not in the exam. I highly hope that at least some of you will still read this material, because in my opinion, this is the most beautiful part of the course, but I understand the last 2 weeks were complicated. It's a pity, but I think it's if you want to be humane, let's put it this way, this is not going to be a part of the course. Now, there is a formula sheet. This formula sheet is for you, but you need to give it to me. And the deadline was actually today. I can wait a bit more. But if you don't give me this formula sheet, it will not be in the exam. I will give you some equations, but I know students, they like to have many equations. This is how they learn. It's fine. So this, this can be 10 to 15 pages. It has to be a PDF file. And your representative has to send it to me. So send it to me. Let's say by Thursday. Then I can add it to the exam and send this exam to the people who produce the exam. Now, it's for you to decide what is this formula sheet. In previous classes, we had these formula sheets. You can take it for them. You can take it from there. But it is the duty of students to check this appendix. So if there is a formula that is simply wrong and you use it in the exam, you cannot complain, oh, this is a wrong equation, blah, blah, blah. So I think there are not too many mistakes in these formula sheets that previous classes used already, but still you might want to check them and find out if there are some. And the way to do it is simply when you learn to the exam, you can use this formula sheet from the beginning. If you send it to me by Thursday, then everyone will know what is this formula sheet. And then you will use it a lot, and then you'll be used to it. And this might be helpful for some of you. Okay, are there any questions?
המבחן יהיה באנגלית או שהוא יהיה בעברית?
So, yes, thank you for the question. So the exam, of course, will be in English, and we will translate it into Hebrew, even though it's very difficult for me because I'm not doing it myself. And all these 4 TAs are not here, but we will manage, and this is especially due to Yossi Ben Zion giving some money for that, and we will do it. And the bottom line is, yes, we will have the exam also in Hebrew. Again, this is very important for some of you. And I respect this totally. It's very important. And the answer is yes, it will be in Hebrew, as well as in English. Anything else? I will be in the exam, and some of the TAs, hopefully, maybe the TA who's now in India, Arkshay, will come back. Maybe not, I don't know. Again, other questions? If not, then let's say goodbye. I wish you very successful studies toward the exam. And
Maybe I have a question.
yes, go ahead.
Is it mandatory to answer the questions in English or Hebrew?
You can answer in Hebrew. Akshay is not going to check the exam. Yeah, so you can answer in any language you wish. It's super important for me that you answer in a clear way. You have no idea how many points you may lose if you write in a convoluted way. Because the reason is very simple. The class is very big, and it's simply a nightmare to check 80 exams or whatever. So you should help us because we are also people, and also because if you don't write tidy, I wonder if you can write a tidy paper in your future. So we want to see your derivation. If you go into some mess, then just copy your derivation again. My suggestion for you always, check towards the end of the solution, check the sensibility of your answers. For example, you check the units of your answer. If the answer is wrong, you find out and you tell me, oh, look, I checked the units and the units are wrong. I missed something. Then fine, I may give you some points for your effort. If you give me an answer where the units are wrong and the answer is so stupid that there's no point in this answer from physical point of view, then I'll give you 0. So it's very natural if you have a long calculation that, sometimes you forget some symbol. It's natural. Also, I do these mistakes. But you can find these mistakes rather easily and admit them. Why do you need to admit them? Because when I get a stupid answer, some students say, this is because I lost something on the way. I lost an omega, I lost a C, I lost something. It's a small thing. But another way to look at it is that you don't understand what you're doing, that eventually you get a stupid answer. So I don't know if you know the physics or you made an error that is human. So simply check these things, and then I'll be merciful when I check the exam. Look at some limits of the solution, like special limits that you can always think, for example, in our formula with this w to the power 4, you can say, oh, look, limit w equals 0, there is no radiation, and this is expected because then we are in statics. Something like that. If you write it nicely, and it helps me understand that you understand the material, and it does help, at least me. Not that I'm going to check the exam, but this is the spirit I'm going to give to the people who are going to check the exams. I'll check some of the exam, but not all of it. Another question? Okay, if not, then thank you very much for listening. And again, good luck in your exams.
Thank you, Eli.
Thank you, Eli.
Thank you.
Thank you very much.
תודה
Thank
רבה.
you.
Ciao.